Okay, welcome back everyone, and we're going to get started with our final two talks for the morning session. So it's a pleasure to welcome Gary Tan, who's coming to us from McMaster, who will be speaking to us about symbolic-numeric techniques for improving structural analysis of DAEs.
Yeah, thank you, Chris. So I got a cold last week, so I may make a funny sound, so please excuse me. But I can assure you that you won't recognize me for my voice the next time you see me. Okay, definitely no. So today I'm going to talk about symbolic numeric techniques for improving the structural analysis of DAEs. So first I need to explain some terms. So DAEs is from differential-algebraic equations. So they arise from chemical engineering, electrical circuits, astronomy, so lots of disciplines. So structural analysis method perform analysis on these DAEs to figure out the characterization properties of these systems. And these properties give guide to the numerical solution methods. So today what I'm going to do is like the following situation. So imagine in your childhood, you have a very interesting toy. You play it day and night. It's just fun. Okay, but so one day it just breaks down, and then you're very upset, disappointed, and you go to your dad, say, "Can you fix it for me?" So today I'm going to do is something like how your dad fixes your toy. So the thing is how to put things back to order. Okay, the toy I refer to here is just the structural analysis. So in my slides, we want to do some maths together. I hope the philosophy people may find this talk interesting and inspiring, because it's a good illustration of how to make a difficult problem, how to tackle a difficult problem by using a not very sophisticated knowledge. So basically just first undergrad calculus. Okay. So this is an illustration of, so for some research, it's not that, the more difficult, the better, okay? So if you can bring down the difficulty level, and then the research can be more accessible, and it can reach more people. So my talk will first of all introduce what are DAEs, and overview structural analysis method called the sigma method. Then I explain why it fails. Then, most importantly, how to make it work again to fix your toy. I provide two conversion methods. And last, we'll give some concluding remarks. So what are DAEs? So take a simple pendulum in Cartesian or coordinate system. So we have a 3x3 system. X, Y, lambda are the variables. So we have two differential equations, A and B, and algebraic equation C. So X and Y are differential variables, lambda is algebraic. So the first point I want to make today is that DAEs are not ODEs. Why is that? So let's write this problem into our favorite ODE form, y prime equals fty. Let's see what happens. So for the first four equations, it's emitted from the equations A, B. Okay? So these are the F1, F2, F3, F4. But how to get F5? So how to interpret the lambda prime in terms of these T, X, Y, U, V lambda. So this is non-trivial work. So you really need to take a pencil and paper to figure this out. It's not easy. So this is the first difficulty we have for DAE. The second difficulty is that even if someone gives me this F5, can we solve this ODE? Mathematically, it's true. However, as you integrate this ODE, the error propagates. And then this pendulum would slowly drift off its trajectory. So that is, the solution no longer satisfies equation C and C prime. So it's not the solution. So if you integrate it, you don't get the solution. So if you use a pencil paper work, you can see that you can differentiate C 3 times to get this mysterious F5, okay? Which gives the expression for lambda prime. So this brings up an important concept in DAE theory. It's a differentiation index. So that's the minimal time of differentiations that you can interpret it as ODE. So y prime equals FTY. So for pendulum, in this case, it's index 3. So the goal for DAEs first is to identify the constraints. And then the second task is to find consistent initial values so that you can start the integration. So in this case, you need to find x prime, y prime such that they satisfy the obvious constraint, which is C, and there's a hidden constraint called C prime. So you need to provide values such that these two equality holds. So structural analysis is, can do this work. So it's a preprocessing stage. When you preprocess the system, you find out the structural index, you find the degrees of freedom, and you figure out which variables that need the initial values. And it also gives the constraints. So by taking all these information together, you come up with a solution scheme. So among many structural analysis methods, the two popular ones, first one is a Pendulitis algorithm. It's a graph-based algorithm. It's not easy to perform. The second one, we focus on the second one, it's John Price's sigma method. So it's easy to apply, it's easy to perform, and today I'm going to show you how to do this by just some simple pencil paper work. You can figure out the analysis for a small problem within just a few minutes. Okay? So these two methods can succeed on many problems of interest. So they succeed on most practical problems. But however, it's not totally flawless. It's not perfect. Sometimes it fails. So today I'm going to show you how to make it fail, but most importantly, how to make it work again. So I'll focus on this DAE problem. So it's a general form with the n differentiable equations in n state variables. Okay? So it's very general. So the differential operator can appear anywhere, and the derivatives can occur implicitly anywhere in the formulation. So we don't restrict ourselves on the order nor on the index of the DAE. So the sigma method is this. So for by n problem, we construct a matrix. So each entry of the matrix is the highest order derivative of a variable in an equation. So take the pendulum here. X appears the second derivative in A, so we put 2 there. Lambda is not differentiated, so we put 0. If some variable does not occur, we put negative infinity. So this is the case for y. So y in the first row is negative infinity. This is the first step. The next task is to find the 3 positions, 1 per row, 1 per column, such that you maximize this sum. So in this case, is those entries in blue, or another one in red. So this totally, thanks you. Yeah, thanks, Mark. So the sum of this value, we call the value of the signature matrix. And these 3 positions, we call it the highest value transversals of sigma. In the next step, we associate with each equation and each variable with the non-negative integer, which we call offsets. So we have n offsets for equations and n offsets for variables. And then from these offsets, they need to satisfy that inequality. And the quality must hold on the HVT. So those positions give the maximum sum. So from these offsets, we can get the information of a structural index we can get the degrees of freedom of problem. And there's a theorem saying if my method succeeds, then the structural index gives an upper bound of a differentiation index. Okay. And in most cases, they're the same, but not for all. So for this success, I need to explain this later. So now take the pendulum again. We have offsets for each variable and each equation. So from these offsets, I know the value of sigma is 2, which is degrees of freedom, and it's an index-free problem, as we knew before. So from these offsets, we know how to come up with the solution scheme that we solve DAE by stages. So each stage, we solve some equation for some variables or derivatives. So again, take the pendulum. The first stage, -2, we solve this coordinate. Okay? And the next stage, we take these known values, plug into here, and we solve the velocities. And the next stage, we solve a 3x3 linear system in terms of x second, y second, and lambda. And for the positive stages, each system is linear, and we solve a 3x3 linear system. So I mentioned the success of the analysis. What does that mean? It means that if I can solve the DAE up to stage 0, then, and if we can determine those derivatives uniquely, then we say the method succeeds. So we need to use this system Jacobian. The Jacobian, each entry in this Jacobian is a partial derivative of each equation with respect to some derivatives. So recall the stage 0 system in the pendulum is a linear one. There is a linear in x second, y second, lambda. So I can write it in this linear system. So the pre-multiplying matrix of this system is exactly the Jacobian. So a restatement of the theorem above is the following. So if the Jacobian is non-singular, the uniqueness and existence is guaranteed for this DAE. Okay, so we can solve this DAE locally. So for pendulum, the determinant of the Jacobian is not 0, so the method succeeds. So this seems so simple to be true, right? So we don't do many things and we figure out the index and figure out how to solve the DAE. So it seems not straightforward. So let's make it fail. So this is a simple linear invariant, a time invariant system. You see the x prime minus ty prime in the first equation, and x minus ty in the second one. Seems ominous. So if a hunch that something bad is going to happen. Sure. As you expect, you get a Jacobian, which is singular. So method fails, just for this simple example. But how to fix it is also simple. We differentiate the second equation and add its opposite to the first one. Then, from this new equation, I replace the first one. So I don't have this one anymore. I have this one and this one. So no derivatives. Apply the analysis, gives the Jacobian. Determinant is -1, not 0. So the method succeeds. So the fix is simple. Another simple fix is I introduce a new variable z and plug it in. Okay? I plug it in, I eliminate the x in the first equation, and then I apply the analysis again. It gives the determinant 1. I have to type it there. So the method succeeds is index 2, and then we use this one to recover the original x. So again, it's a simple fix. So the problem statement is like this. If someone gives me a system we apply the structural analysis. However, it generates an identically singular Jacobian. So what should we do? We want to fix this failure not by just observing these equations and look at the whole equations, figure out one by one. We don't want to do that. We want to figure out in a systematic way. So the failure, people are aware of this failure, so it's not classified, it's not untold secret. People know this, we just don't know how to fix it and what causes it. So it wasn't until last year we find out two conversion methods. One is focuses on the linear combination of equations. We call it LC method for short. Another method is expression substitution. We call it ES for short. So both methods can kind of fix your toy. So we have this conjecture. If my value of the sigma is decreased, then we might have a better problem formulation on which our method succeeds. So let's take a look at the first method, the LC. Okay, we have this DAE, apply the analysis. No surprise, get a singular Jacobian. Okay. So the value of sigma is 1. It fails. It just fails. So what does it mean? It means the Jacobian singular, but what's the meaning for it being singular? So this is a definition of the Jacobian. It's a partial derivative of equations with respect to some derivatives. So this is a Jacobian. If it is singular, then we can find the vector in the symbolic form from its co-kernel. Okay? So look at this view. Observe that it does not depend on what's down there. It does not depend on these derivatives. So this means if I take the linear combination of these equations, just using the product rule you learned in the undergrad, you can prove that the resulting equations from this linear combination does not depend on this derivative as well. So if I replace one of the existing equations by this new equation, we can prove it. We reduce sigma. We cannot pick F3 because F3 is differentiated here. If we replace it, then it's gone. We cannot recover it back anymore. However, for some of them, you can recover. Let's take F4. So we replace F4 by this new equation, apply the analysis, gives this determinant. It's not identical to 0. So if it's non-zero, our method succeeds. In this case, the value of sigma is less than before. So this is an important fact to note because we will use this all the time. So we can easily recover the original equations because the corresponding entry in U is not 0. So we can easily recover the original equations so nothing is lost. So this is the outline. We get a symbolic form of Jacobian. We find the vector in its co-kernel. Then we derive something to figure out which equation we can replace and take the linear combination of the existing equations. So then we replace one of these equations by the new one. So the theorem says if some order conditions is satisfied, then it's guaranteed that I can decrease sigma. So this means the highest order of xj in U. So if the conditions are satisfied, we can reduce it and get a better problem formulation. If the resulting Jacobian is still singular, we can keep repeating this procedure, proceeding iteratively, and since the value of sigma is decreased by 1 each time, for sure, at least, so the number of operations is at most value of sigma. So you won't be doing this infinitely. So what's inspired by this method is the following. So we take a combination of equations. So equations correspond to rows. So how about columns? So columns correspond to derivatives. Yes, you can. So that's why we have the second method, the ES method. So the ES method takes a combination of variables and derivatives. So like this problem. But for this problem, our LC method doesn't work because it does not satisfy the order condition. Okay? Applied analysis fails, of course, right? Otherwise, I don't have story to tell. So again, this is singular. By observation, you have this negative x1 prime minus x2 second, x1 plus x2 x2 prime. It looks similar, so there must be some nastiness there. So if LC method does not work, let's figure out something else. So the ES methods proceed as the following. First of all, it processes the structural analysis result. It figures out, it computes a vector, this time from the kernel of the Jacobian. Okay? And figure out these sets and these indices. The purpose is to identify the common expressions. So now we introduce a new variable to represent these common expressions that we kind of dig it from the structural analysis result. Then we perform expression substitutions. So we kind of substitute this one for this, substitute this for this. Basically, just plug them in. So let's see what happens if we plug them in. So a lot of things cancel out. Okay? That's expected. That's what we want. Then we get this system. It's neater than the previous one. Okay? We also need to append these equations that prescribes the substitutions. So this equation tells me I substituted y1 for this common expression. Okay? Then we apply the analysis. We reduce sigma. The determinant is no longer identical to 0. So if we succeed, if this is not 0, it's index 2. Because f2 is differentiated. So the outline is to find the vector from the kernel of the Jacobian, figure out the common expressions, replace them by the introduced variable, simplify the equations, append the equations that tell you how to substitute things, then get a theorem. So it's guaranteed we can reduce sigma if these order conditions, again, are satisfied. So we have made some progress. We arbitrarily mess up the DAE to construct those ones on which the method fails. Then we kind of put things back by applying those methods we developed. So we fix things in a systematic way. But for practical problems, we fix these. The robot arm is an index 5 problem. In the beginning, we report index 3, which is wrong. Then we fix it by both methods. These two problems, transistor amplifier and the ring modulator, come from electrical circuits. So they are in the solution, they're in the test set of initial value problems. So this is by University of Barry. This one is pretty new. It's a couple DAE, but actually it's just a linear constant coefficient DAE. Our method fails in the beginning, reporting index 2. However, it's index 3. We apply the linear combination method twice to fix it. We report index 3. The last one is a little bit special. So Reisig says he has a class of DAEs that are differentiation index 1. However, the structural analysis method reports arbitrarily high index. That is also well known in the DAE theory. But we don't want to do that. It's not good. Because if someone gives me an index 1 problem, I say it's index 10, then it will upset them. Okay? I exaggerate the numerical difficulty. I don't want to do that. So we apply the linear combination method again. Very simple. Just F1 plus F2. That's done. We get the correct index again. It's index 1. So some concluding remarks will identify the structural analysis failure. So it reports an identically singular Jacobian. We come up with the 2 conversion methods, which are the contributions. One is the LC method, takes a linear combination of equation. Next one, ES method, it performs expression substitution. So we the main goal, the common goal of both methods is to reduce the value of the signature matrix. So we have this MATLAB package that performs the structural analysis of DAE. It can be downloaded here. It's easy to use. We combine our package with the MATLAB symbolic toolbox. So we kind of come up with a prototype implementation of these conversion methods to just systematically fix the problem if the analysis fails. So now it comes to the end of my talk, and thanks for your attention.